Yeah, the floor is yours, Etienne.
Okay, thank you very much for the presentation and for inviting me. So this work was done with Fabian Essler in Oxford University. So I'm going to start with some recalls on integrability. So in an integrable models, the eigenstates are labeled by a set of rapidities lambda 1, lambda n. And you have a kind of free theory-like representation for the eigenstates as well as for the eigenvalues. So by free theory-like representation, I mean that you have such an expression for the eigenvectors and the eigenvalues. And in these expressions, the rapidities seem to be independent of each other. But you have an interaction that is captured in the default quantization condition that have to be satisfied by the lambdas, which you also call the Bethe-Ansatz equations. So if the right-hand side is equal to 1, which is the case for three theories, you recover the usual quantization condition for the rapidities. But if you have some interaction, then all the lambdas will depend on each other. So this representation is very convenient for computing the spectrum of your model in very large system sizes. For example, for several thousand of sites, because you can solve the Bethe equations and simply implement then the value of the energy levels. And also, in the thermodynamic limit, you can recast all these equations in terms of integral equations on some root densities lambda that replace the Bethe roots. So there are actually some inconvenient truths about this nice picture. The first one is that the Bethe equations can be difficult to solve. So in some models, you have a lot of different solutions to the Bethe equations, and so it's actually a lot of work just to classify them. The second problem is that although the eigenvalue representation is very convenient for large L calculation, it's not the case for the eigenstate. So, for example, if you want to determine anything that is intrinsically related to the eigenstates, such as correlation functions or entanglement entropy, for example, you cannot just take this formula here and put it in a computer for large system size. And thirdly, although you have an explicit expression for the eigenstates, the correlation function within these eigenstates are actually difficult to compute. And so in the end, this is what you want to do. And so as a consequence, they have often been studied through a mix of field theory and Bethe-Ansatz techniques. For example, if your theory is critical, you can study it with conformal field theory. And so within CFT, you can show that the critical exponents that are associated to these static correlators are exactly connected to the finite size correction to your energy levels. So then you transpose a problem of computing the correlation function, which is something that is intrinsically related to the eigenstate, onto a problem that only involves the eigenvalues, which are much simpler to compute. So this is the same for GHD, generalized hydrodynamics, that gives the large x and t limit at x over t fixed of this quantity here. And so in this case, you don't need any information on the eigenvectors. You just need to know the conserved quantity of your eigenstates. So if you don't use any field theory argument in order to simplify the calculation, there is any ab initio calculation of the correlation function directly from the Bethe-Ansatz is actually much more difficult to do. So, however, in the past decade, there have been a lot, so significant progress in the computation of this correlation function by writing it as a spectral representation. So let's say that you have an eigenstate lambda of your system, and you want to compute the two-point function of some observable, separated by a distance x and a time t. So the idea is simply to insert here a complete set of eigenstates, mu, so that you can recast this correlation function as a sum over all the eigenstates of your model of a certain form factor here, so a matrix element of your observable between two eigenstates, times a phase that will involve t and x. So what makes this representation appealing is that you actually, for several models, you actually know an explicit and compact expression for the form factor here. So in this expression here, actually all the terms are known. Moreover, there is a kind of nice physical intuitive interpretation of this. So if you represent your averaging state by a set of particles, you can view the mu as excitations above this set of particles. And so you would like to think that the closer mu will be from lambda, the larger will be the form factor. So you would like to think that this sum over all the eigenstates will be actually truncated to just a few excitations of mu above lambda. So however, there are several difficulties in computing this sum. The first one is that there is an exponential number of terms in this huge sum here, which means that, for example, you can have some terms that are completely negligible in L individually, but they can be, for example, much more numerous. So in the end, maybe they will be actually dominant. The second problem is that the form factors typically they vanish when L goes to infinity. So if you want to compute the thermodynamic limit of this, you cannot just take the thermodynamic limit of each of the terms in the sum and then compute the sum. And thirdly, the form factors are actually quite intricate function of the beta roots here. And in particular, there are poles in the form factor whenever there is one of the lambda that comes close to 1 mu. So obviously in finite sets, the form factor cannot be divergent. So so you will never have exactly one lambda that is equal to 1 mu. So this is why the picture here that I drew is a bit too simplified, because in fact the beta equations will slightly shift all the beta roots as soon as you modify one beta root here. So in fact here the two beta roots will differ by something that is 1 over x squared typically. Okay, so in order to compute this sum, there have been several approaches. So the first one was a numerical approach that consists in implementing numerically this spectral sum. So this relies on the fact that you have some determinant representation for the form factor that you can evaluate with the computer in a very large system size, like several hundreds of sites. And it also relies on the fact that you can actually truncate this sum to a small number of states. Because if there is still an exponential number of states that counts this sum, then it will not be very convenient to do that. So what they do in the first papers, they considered a 0 temperature ground state. So it's a state where lambda here is given by all beta roots fully packed around the origin in a symmetric fashion. And so they considered mu as only a few particle hole excitations above this state. So it means that they pick one of the beta roots of the state lambda, and they move it elsewhere in momentum space. And the jump here can scale with L, so it can be of macroscopic amplitude. So in order to check that they do, that these states that they consider do give the full, or do approximate well the correlation function, they check the value of some sum rules. So these sum rules are some identities that have to be satisfied by the correlation functions, or more precisely by the Fourier transform of the correlation function. And so then you can simply evaluate these sum rules, these identities, with the few states that you took into account, and just check that these identities are indeed satisfied. And so in this case, what they obtain is that they are satisfied at more than 99%, which is a very good sign that indeed the states that they take into account are enough to saturate the sum. So for example, so they applied this to the x-axis mid-chain, and they actually obtained excellent agreement with the CFT predictions. And also the dynamical structure factor, so which is the Fourier transform of the correlation function, actually gives a remarkable agreement with some real scattering experiment on the real material. So on the analytical side, there are several approaches. So the first approach was a kind of ab initio calculation of the asymptotic expansion at large time and space of the same state, so 0 temperature ground state, in several interacting models. And so surprisingly, what they find in this case, they find that the states, the intermediate states, mu, that contribute to this asymptotic expansion are actually very different than the states that I described before, because it consists in what we call the soft modes that completely give the asymptotic expansion. So the soft modes are, in a sense, some small rearrangements of the particles of the averaging state. So you have to allow for as many as particle hole excitation as you want. but it's just small particle hole excitation. So it's, the jumps here do not scale like air. It's smaller than air. And you also allow some processes that come from one of the Fermi point to the other one. So more recently, there was another approach which is called thermodynamic form factors. So it consists in trying to take the thermodynamic limit of the form factor directly before taking the sum. So in fact, in order to do that, they have to do a kind of phenomenological summation of certain soft modes in order to be able to take the thermodynamic limit. And so there is a kind of obvious loophole in that, because here they have to neglect the x and t dependence that comes with these soft modes. And in the case of the large x and t behavior, these soft modes were precisely observed to give the dominant contribution. So here it seems that there is a kind of contradiction that is not entirely clear how to reconcile. So in these three examples, I've illustrated the fact that it's actually not clear which states contribute in the sum and how you can really organize this spectral sum. So the open questions that I'm going to try to answer in this talk are the following one. So first, which excitations actually dominate the correlations, for example, at late times at large distance? But also, what is the natural expansion parameter that you can have for the correlation function? Because in any case, there is few hope that you can obtain an expression at all x and t and all eigenstates. So in any case, it will be expanded in a sense. So for example, in the numerical approach, this was expanded in the number of particle hole excitations. But in the ab initio calculation, this was expanded at large x and t. So the question is, what is actually the natural expansion parameter? Does it depend on the eigenstate? Does it depend on the observable? And so in this talk, I'm going to present two calculations. So I'm going to answer these two questions in two specific examples where you actually have very different answers. So the first case is the sigma x correlation in the transverse field Ising model. And the second case I'm going to talk about are the density correlation in the Lieb-Liniger. So one of these models is free and the other one is interacting, but the true difference between the two calculations is actually in the observable. So the sigma x are semi-local observable, whereas the density are local observable. So in 1D QFT, the locality is defined by whether or not you pick a phase where you do some analytic continuation of the product of some of two operators. And so if this phase here is 0 when you take the product of an operator A with the operator that creates particles, then you say that the operator is local. So this is the case of sigma z in the TFIM, but also sigma z in the XXZ and also the density in Lieb-Liniger. If this phase is non-zero, for example, if it is 1/2, then you say that it is semi-local. So this is the case of sigma x in the transverse field Ising model, but also the field in Lieb-Liniger. So what we find is that actually the states that contribute to the correlation functions are completely different for local operators and semi-local operators. And this comes from the fact that the structure of singularities is very different in the two cases. So for local operators, if you take the form factor of a local operator A between two eigenstates whose rapidities differ by some epsilon, you are going to have a pole of order n here, but also a lot of zeros, so n zeros in the numerator. And so in this case, what we find is that an expansion in the number of particle hole excitations is actually possible. And the excitations with macroscopic amplitude are needed in order to compute the correlation function. However, for semi-local operators, the structure of singularities is very different because you still have this pole of order n, but you don't have any zeros in the numerator. And so in this case, what we find is that you cannot do an expansion in the number of particle hole excitations, and instead, you have to allow for all the modification of the Peto roots of your averaging state. But however, you can restrict yourself to only mesoscopic amplitude. So it's, I'm going to define that after. So it's less than macroscopic, but larger than microscopic. Okay, so I'm going first to describe the calculation for the semi-local observable in the TFIM. So the TFIM is a model for L spins with, for example, periodic boundary conditions that interact through a sigma x interaction here. And also there is a magnetic field interaction here in the z direction. So what makes this model interesting is that it is actually a free fermionic model for all values of h with a non-trivial dispersion relation. And so there is a phase transition at h equals 1 that separates two phases, an ordered phase and a disordered phase. So the eigenstates, they split into two sectors, one where the rapidities are proportional to the to integers, and the other one where they are proportional to half integers. So you remember that at the beginning I said that the form factors are, the singularities of the form factors are regulated in finite size by the Beto equations. So in this case, what happens is that the form factor will couple only states between two different sectors. So the 1/2 here will play the role of the regularization. Okay, so let's assume that we want to compute the correlation function for sigma z. So these are very simple because it's local in terms of the fermions. It involves only product of two fermions. So then you can write correlation function for them quite easily with a Wick theorem. However, if you take sigma x, this one is not local in terms of the fermion. It's expressed as a chain of fermions. And so then you have two possible approaches. Either you stick with this fermionic representation of sigma x. In this case, you end up with some Riemann-Hilbert problems. So this was done for the impenetrable Bose gas, but it was not done for the TFIN. Or this is what you are going to do. You do some sums over form factors.
Wait, but it was done for instance, for XY model.
Yes, indeed, for XY.
Yeah, yeah, which is TFM is just one particular case. So.
So it was for XY, but with so I don't remember exactly I think there is one parameter that was fixed to something in the XY model. I don't remember exactly which one, but there is one parameter that you can vary that is not taken into account in this case.
But I think it's possible, I mean, I can't say from the top of my head, but I think it's possible to present like total correlation function, let's say sigma x as for Fregon determinants, let's say.
Sorry?
So you can find closed expression just for sigma x correlation function as Fregon determinant.
As Fregon determinants.
Right. The same as in.
Yeah. Since it is equivalent to free fermions, you can certainly apply the same formula.
Yeah, and the same for Ising as well.
To determine the large XNT dependence. But what we want to do in this case is really applying these sums over form factors, because so first there is some hope that it will actually be simpler than solving the Riemann-Hilbert problem, because this is actually.
Oh yes, that's I totally agree. Yeah.
In order to obtain the large XNT dependence. Mm-hmm. And also because it's a bit more physical, if you want. I mean, we can really understand which states will contribute, and so we can understand more. Also, it's also a good starting point to understand the spectral sum here in this case, in order then to apply it to the interacting cases. Mm-hmm. Okay, so in any case, so the sigma x correlation function. So in this case, we are going to write it as a spectral sum. So let's say that we want to compute the sigma x correlation function within an eigenstate given by rapidities q1, qn. So the two-point function is expressed then as a sum over p1, pn here, and the form factor has this given value here. So you see that the form factor is very intricate as a function of the p's, and so in particular, so obviously it does not factorize at all with respect to the p. But also, let's say that you want to compute a one particle Hall excitation only. So you would like to fix the values of the p to m-1p to something, and then you vary only the value of p1. So what you are going to have here is that p1 is going to cross all the q's of the representative states. So you're going to encounter a lot of double divergences here. And so if you would like to transform this sum into an integral, a one-dimensional integral, essentially the integrand of the integral will be divergent everywhere on the real axis. So this already shows that doing only one particle Hall excitation calculation is actually not that simple. And so what we found to be the right way of computing this sum here is to apply a partial fraction decomposition to the form factor. So the idea of a partial fraction decomposition is to take a polynomial when you have a polynomial over x, or a polynomial over x divided by a product of some monomials here to a certain power ai, then you can write it as a polynomial of x plus some monomials here, and you also have to allow the nu here to be smaller than the ai.
May I ask you a quick question?
Yep.
So with these p's and q's, they can't take exactly the same value, right? That's what you showed on there.
That's, so the p are quantized this way and the q this way.
Yeah, so there's never actually hit a pole.
Yes, exactly. But when you transform it into an integral, then this 1 over 2L here will not appear. So I agree that in finite size, there is no problem. There is no divergence in anything. But if you want to take the thermodynamic limits naively of the equations, you are going, this regulation here are going to disappear. And so in the end, what you are going to have is an integral over something that have a double pole.
Yeah, okay. So it does blow up when you try to take limits. All right.
Yeah.
All right, thanks.
Okay. Okay, so the form factor is a multivariate function of the p's. So what you are going to do is to apply n successive partial fraction decomposition to each of the p. So let's say you start with p1. So you say that this quantity here is a certain function of p1, p2, pn, but without any poles in p1, plus a simple pole in p1 with some function that does not depend on p1, a double pole in p1, and some function that does not depend on p1. Then you do the same thing to each of these functions here. So you take, for example, this one, and you decompose with respect to p2. So you have some simple poles in p2 and some double poles in p2. So in the end, what you obtain is a huge sum here of a lot of factors, a lot of terms that are going to be factorized in p. So it means that each p will actually appear only once in each of these terms here. So however, each q can appear several times. So in these expressions, you are going to have a kind of mapping between each of the p that are represented by white bullets here onto any of the q of the representative state here that are represented by black bullets. So this formulation is very convenient because you can actually compute the spectral sum on each of the term, because the spectral sum is going to factorize as a product of n one-dimensional sums here. So you still have a pole, obviously, but there is only one pole, and so this you can compute in the thermodynamic limit and express it in terms of the dispersion relation. So for example, if you restrict yourself to only large t, this is the value that you obtain for these sums. And so, so you can see that if you have a double pole, then there is a dependence in t here, whereas that if you have a simple pole, you have no dependence in t. And so this means that at large space and time, the leading poles will actually give the leading contribution. So if you focus only on the dominant term, this is going to be given by the one where you have only double poles, this term here. And so when you compute the spectral sum on this, so each of the sum will give a factor like that. So you're going to have this product here. And this, when you take the thermodynamic limit, you obtain such an exponential here that decays with time.
So,
quick question. So do you assume, what do you assume about state at which you perform the summation? I mean, it surely can be true for vacuum state, right?
Yeah, so up to now, so we did not assume anything on the Q, so on the averaging states. The Q, you don't assume anything. In the P there, you have to sum over everything.
Yeah, but for vacuum state, we know the answer, and it's just some simple power.
Okay, yeah, right? Okay. So you assume, if you want, that the Q1, Qn, that there is a macroscopic number of.
So it's some finite entropy state. That's all
yes,
what you assume,
you
right?
have to assume that n scales like n. So if you want that, the root density is non-trivial, because if you take only a finite number of Qs here, the root density will be exactly 0. So in this case, it's a bit of degenerate case.
Okay, cool.
So we are assuming, if you want, that n scales like L. Yeah.
So I also have, I'm trying to understand this kind of fancy A, because it's some function, right? On the previous slide.
Yeah. So these are the coefficients that you are going to obtain in the partial fraction decomposition. So in
But
general,
don't these get more and more complicated as you add more, like add
exactly,
more,
exactly. Yeah.
as you add
So
more
there is a
particles? This becomes like an incredibly complicated function, right? I mean, can you even?
Yeah,
Does it
exactly. Yeah.
help to do this? I
So
guess it does.
what you can do, so I'm going to present just after the next terms. So if you want to compute the next term, so for the leading term, the A is just equal to 1. But if you look at the next terms, so you are going to replace some of the double poles by some simple poles here with some coefficients that you have to compute. And so for example, so this is the value of the A that take this coefficient here. And so, so they are in general a bit complicated to compute. And also they also have some poles in the Q. So it's not the same kind of poles because there is no P dependence anymore, but there is a pole in the Q. So, so it's a bit complicated here, but in this decomposition, you can still compute the spectral sum on each of these terms because the P are still factorized. So when you do this decomposition here, so each time you pick one of the double pole to replace it by a simple pole, you are going to take factor n over L because you choose one of the n Q of the representative states. And so this expansion here is exactly an expansion in the density of particles of the averaging state.
Yes, sorry. So n is kind of the number of downspins or number of excitations, if you will.
N is the number of rapidities in the
Right. Okay, I see.
in the averaging state. So yeah, it will be related to the magnetization. Yeah.
Right. Thank
But
you.
it's assumed to be to scale like L. If you want, you can see this this state here as being a discretization of a root density in finite size.
So you could also create more particles in intermediate states, no? Like why the two ends have to be equal? Or
Yes, exactly. So there is a step that I indeed did not talk about just for simplicity. So indeed here there is a m that is not necessarily equal to n. So in principle you have to sum over m also. So indeed, so there are also terms where you are going to have m equals n plus 2, for example. But these terms, they are going to be subdominants at large x and t. So they are first going to be oscillating and also subdominants in t. In fact, this dominant term here, where you have only double poles, will not be present if you have n plus 2 and n here. So, so you can see in the calculation that it's going to be subdominant. But indeed, there is, in general, there is this term. Okay, so we perform the calculation at order rho square. So it's rho square within the exponential. So you actually have to sum, to take into account some terms here that have a macroscopic number of simple poles. So it's not just these two terms here, but you have to take into account a macroscopic number of terms. And so we obtain this factor in the exponent here with a prefactor that we know out of the rho square. And so this is true for essentially any root density rho here. And so if you focus only on the exponents, then you can actually compute it at all orders in rho and resum the result into a log of 1 minus 4 pi rho of x. So this gives the exponent, the exponential decay for within any eigenstate with root density rho. And so this is a new result. So for example, so if you want to compare this to some numerics, you can take some thermal states. And in this case, the two-point function within this thermal state will correspond to the finite temperature correlation functions. And so since the TFIM is a free harmonic model, you can actually compute exactly the values of these finite temperature correlation function. So with a computer in finite size and compare with the calculations. So here, the red bullets, the red crosses are the exact numerical calculation of the finite temperature correlation function. And the blue lines are the analytic calculation from the form factor expansion. So for static correlators, here we plotted the log of the static correlators in terms of R. And so you see that the agreement is actually excellent. And the only discrepancy, they come from the fact that we know the prefactor only at order rho square. If you take dynamical correlators, so here is the same. So I plot the log of the dynamical correlator as a function of t. And so you see that there is some discrepancy here. And so on the right panel, I plot the difference of the two here as a function of log t. You see that it's essentially proportional to log t. So it means that the subleading correction here is actually a power law in t. So you have a subleading multiplicative correction to the exponential that is a power law. And so this comes from the fact that for the dynamical correlations, there is a point where the epsilon prime is equal to 0, so which is a saddle point. And so in this case, so this equation here, it cannot be true, and so you have to take into account the next term. So this power law, this subleading power law here, is not given by other excitations, but it's just given by the fact that that you have to treat more carefully the saddle point here. But in any case, the exponential decay is absolutely recovered by this formula, because otherwise you would not have such dependence here. Okay, so up to now, I've talked about correlation function, two-point function within an eigenstate, but there are obviously a lot of other problems apart from correlation functions that you can formulate in terms of sums over form factors. So this is, for example, the case of quantum quench dynamics. So this consists in evaluating the time evolution of a certain observable, for example, the mean value of some observable after a sudden change of magnetic field. So for example, you start with a magnetic field H0. So you assume that you're in a ground state of the magnetic field H0, and then you suddenly change the value of the magnetic field to some value of H. And you want to compute the time evolution of this observable here. So you can also, within the quench action method, recast this quantity here as a sum of some form factors, with the important difference that there is an overlap here that you have to compute. So we also did the calculation in this case. So it's a bit similar, but not exactly the same. And so we obtain similar results. So an exponential decay with tau that is known at all orders in rho, and c that
Sorry,
is.
Etienne.
Yep.
So this 0 tilde is kind of the initial state.
Yes. Yeah.
Okay.
The initial state.
Like the pre-quench state, or.
So you have to express the initial state in terms of the eigenstates of your new basis, which is the basis with H. So you have to time evolve, if you want, the initial state in terms of the eigenstate of the new basis. So this is what is taken into account here. Okay, so in this case, so we obtained the time evolution that is written like that here with, so as I said, so tau that is obtained at all orders in rho and c at all rho square. And so rho in this case is given as a function of h and h naught. So essentially it's h minus h naught. I mean, it's of order h minus h naught. Okay, so with this, I answered one of the two questions, which was what is the natural expansion parameter? So for the semi-local observable, in this example, we see that the natural expansion parameter is the density of the averaging states. You can really obtain very uniform approximation in the density if you want by expanding with respect to the density of averaging states. And so if you truncate your spectral sum to n particle hole excitations, what you actually obtain is a correlation function that increases as t to the n. It's a bit like, if you want, Taylor expanding a decreasing exponential at order n, you obtain something that very fast becomes quite bad. And so in this case, you really cannot do an expansion in the number of particle hole excitations, because the expansion will be completely non-uniform and quite bad very fast. So you need actually all particle hole excitations. So it's modification of all the beta roots of your averaging states. But however, the excitations need to be only mesoscopic. So it means larger than any inverse power law in R, but it can be smaller than some epsilon L to the 0. Okay, so this was for the semi-local operators. Now I'm going to talk about a local observable in Lieb-Liniger. So I recall you that the Lieb-Liniger model is a quantum field theory for canonical Bose field that satisfies the following canonical commutation relation. So the Hamiltonian contains an interacting part here proportional to C with 4 terms. So this is solvable by the better ansatz. You can write any energy level as a sum of the lambda square, where the lambda satisfies the better equations here. So the observable that we are going to be interested in is the density operator, which is psi dagger psi. So it's the density of real particles. So obviously it has nothing to do with the metabolic density. Okay, so if you want to apply exactly the same strategy as before, so you write your two-point function for sigma as a spectral sum over some form factors here. So as before, we know some expression, some compact expression, determinant expression for the form factor here. And if you want to apply a partial fraction decomposition again to the form factor, you actually find that the leading term with only the double poles that I showed you before actually vanishes. And if you look at the next leading terms, the ones with some simple poles, they actually have high order zeros in the numerator with some macroscopic power here. So it means that all the terms that actually gave all the exponential decay before, and the exponential decay was actually, so we saw in the numerics that it was essentially almost all the correlation at all time. All these terms here, they will be extremely small in the case of a local observable. So it's already sign that the form factor, the sum over the form factors will actually be completely different in this case. So the next observation to do is that if you consider n particle hole excitation, so a mu that's whose beta numbers will differ from those of the lambda by only n positions, I mean n beta roots will be different in mu compared to lambda, then the form factor is actually of order 1 over c to the 2n-1, where c is the strength of the interaction. So it means that if you expand everything at order 1 over c squared, so the beta equations, the form factor, the phase here, so everything, then you automatically truncate your spectral sum to only 1 and 2 particle hole excitations. And so in this case, this truncation is not an approximation, it's not an arbitrary choice. It's really something that directly follows from the fact that you expand everything at order 1 over c squared.
Yeah,
Okay,
but doesn't mean that if c goes to infinity, it means it's kind of, we go back to free fermion.
Yes, exactly. So since we explained that order 1 over c squared, it means that the leading order is given by the limit c to infinity, which is the impenetrable Bose-Gas limit. And so this is equivalent to free fermions. And so in this case, you can compute the correlation function of the density operator quite simply within any eigenstate rho of lambda, as well as the dynamical structure factor that is given by this formula in terms of rho. And so then the question is, what happens if you want to take the 1 over c and 1 over c squared correction to these results? Because in this case, you are going to have to perform a proper spectral sum here with 1 and 2 particle hole excitations that are not as trivial as the free fermion case. So for example, so this is what you have, the spectral sum only for 1 particle hole excitations. So you have here 2 sums. So one of the sums is the sum over the particles of the averaging state, and the other sum is the sum over the holes. So this is which particle you take and where you put the particles in the intermediate state mu. Between the square brackets here, you have your form factor expanded at order 1 over c squared, and then you have the phase here expanded at 1 over c squared. So it's the same for 2 particle hole excitations. You have this expression for the spectral sum. So you have now 4 sums. And so 2 sums over the particles and 2 sums over the holes with the form factor and with the phase. So now you would like to compute the large N limit of these expressions here. So and what we actually found is that if you compute the thermodynamic limits of the 1 particle hole excitations and the 2 particle hole excitations separately, you find actually a divergent result in L. So each of these sums here, they actually diverge when L goes to infinity. So if you want to take into account only 1 particle hole excitations, you would get something that will grow with L and that will diverge. So however, if you take into account everything in the correlation function at order 1 over c squared, so then it's the sum of the 1 particle hole excitation and the 2 particle hole excitations, then the divergences exactly cancel out and you obtain something that is well defined. And so these actually give the correlation functions at all space and time at order 1 over c squared. So for example, just to show some of the results. So if you take the dynamical structure factor at 0 temperature, so this is at order 1 over c squared, the wood density is quite simple. So it's simply something that is constant between two values minus capital Q and capital Q, and that is 0 elsewhere. And so you find this contribution here to the of the one particle Hall excitation to the dynamical structure factor at order 1 over c squared. So you have the free Feynman limit here, and then you have some log over c and log square over c squared, with some thresholds here, omega plus and omega minus. So as it must be at 0 temperature, the one particle Hall excitations have to be non-zero only between these two thresholds here, and then you have some logarithmic singularities near the thresholds. So if you take the two particle Hall excitations, the expression is a bit less nice, but you have this integral representation in terms of the various parameters that you have. And so this will be generically non-zero for all values of Q and omega. So there are some regions where it's exactly 0, but the regions where it's non-zero is much larger than for the one particle excitations. So for example, so this is what we obtain when we plot these functions. For C equals 4, the one particle Hall excitations here is 0 outside a certain range, and you have some logarithmic singularity. The two particle Hall excitations, you also have some logarithmic singularity within the same range, but you also have something that is non-zero outside. And so, an important observation here is that the two particle Hall excitations, even if C is not that large, is actually already much smaller than the one particle Hall excitation. So this is good news that you can actually do this expansion here in 1 over C, because the second term is already much smaller than the first term. So in order to check our results, we actually passed several tests. So for example, there are some CFT predictions for the static correlators of the density. So CFT predicts that you have this 1 over x squared decay plus an oscillating term here divided by a fractional power of x with an integer parameter k that depends on c. So when c goes to infinity, this k goes to 1. And so when you expand that over 1 over c, 1 over c squared, this fractional power of x here is going to become 1 over x squared times some logarithms. So the 1 over c correction to the k will give a log over c, and the log square over c squared. But the 1 over c squared in k will give a log over c squared. So since we expand everything in 1 over c, we cannot see this fractional power, but all we can see is this 1 over x squared times some logarithms. And so we actually indeed recover this expression here. Next, there are also some predictions for the logarithmic singularities in the dynamical structure factor near the thresholds with nonlinear Lagrangian liquids. So this we also recover correctly. And finally, there is the numerical saturation of some sum rules that you can check. So we checked the value of the F sum rule, which is the integral of the S of omega Q times omega. That has to be proportional to Q squared. So in this case, we have to integrate this equation, this equation here. And so we obtain indeed numerically, essentially almost 100% saturation of the sum rule at order 1 over c squared. So the conclusion of this calculation is that for local observable, illustrated with the density operator in Lieb-Liniger, we can indeed do an expansion in the number of particle Hall excitation, but it's a kind of mix between an expansion in the number of particle Hall excitation and a 1 over c expansion. Because, as I said, so if you take only the one particle Hall excitation at a fixed value of c, you actually get something that is divergent in R. So you have to take at the same time the one particle Hall excitation and the two particle Hall excitation at order 1 over c squared in order to get something that is non-zero. But this approximation is in fact essentially uniform in space and time. So it means that contrary to the semi-local observable, you don't have something that becomes diverging at late time or at large space. So moreover, the fact that you can do this expansion means that in this case, you can, in the spectral sum, you can restrict yourself to a polynomial number of states, but with, however, macroscopic amplitude. And so we are going also to apply this to some quantum quantities in Lieb-Liniger. So I recall that for semi-local observables, on the contrary, so this was illustrated in the DFIM with the sigma x calculation. In this case, you cannot do an expansion in the number of particle hole excitations because each truncation to a finite number will actually be completely divergent. And so instead, in order to obtain the right, the exponential decay with the correct exponent, you have to allow for all the modification of all the particles. And so, but you can restrict yourself to only mesoscopic amplitude of excitations. And so in any case, this means that you have to take into account an exponential number of states in your spectral sum. So thank you.
Okay, thank you, Etienne. And the questions.
Right. So in your introduction, you mentioned some discrepancy for with result of for finite temperature result for density correlation function. This one. Panfield and Ardis and Kozlowski. Right. So can you add something with your approach to that?
Yeah, so, okay, so first, so there is an important difference. So the thermodynamic form factors were applied to a generic root density without jumps, so continuous root densities. And so this calculation here is obviously only for zero temperature.
No. I'm asking about second. Yeah.
Where you have a discontinuity. So, so it's not directly in contradiction, but it's just that at least in the case of zero temperature ground states, you see that you have a very important space and time contribution from the soft modes that is completely neglected in this case. And so in our calculation, we see that indeed, so the same contribution here will actually give some, do not seem to be negligible at all.
Right, but
I just wanted to make...
by doing that, you lose something.
Right, but
not at zero temperature, even for generic root density.
But for instance, if you apply your approach for density correlation function in Lieb-Liniger, but for finite temperature, there is at least CFT prediction, which just saying that every x in the denominator you should replace by something like sinh x, right?
Yes, indeed.
Can you see it from your approach?
So we didn't look at finite at the CFT prediction. So so we didn't look at this yet. Yeah.
Why I'm asking, because the story of soft modes, it's indeed the divergence with system size of let's say form factor between like vacuum and the first the simplest form factor is like for zero temperature is like 1 over L to some power, let's say, and here when you have finite temperature, it's exponentially small, and that's why these authors use this instead of soft modes, because basically you don't have soft modes in terms of form factors. So if you look at your form factor, it does not die as 1 over L to some power at finite temperature. Because your root density are so spread that even if you like put with the same quantum numbers, you still have exponentially small. And that's why they say, so I think the logic was like this. We need, like, contrary to zero temperature, we need exponentially many soft modes to cure this very strong orthogonality catastrophe. And this, as I understand, must result if you include space-time dependence in this exponential behavior. But I'm not sure about this.
Again, so what we see in our calculation is that there is an ex-ante dependence that comes with that is not trivial. But then maybe that in some limits, in some particular limits, it will be some dominance. But it's not clear. It's not clear. In any case, you clearly lose something by neglecting the ex-ante dependence in that.
Also about 1 over C corrections, I'm not sure, probably you know, but there were around 2006, at the beginning of this nonlinear Liniger liquid, there was work by Brandt and Cherny.
Yes, exactly.
Yeah. So they also computed this stuff, and yeah.
So they computed, so Brandt and Cherny computed the large steel mid, so they computed that for 0 temperature. So they computed the dynamical structure factor only for a rho that is given by this when C goes to infinity, if you want. But in any case, so the generic rho calculation when C goes to infinity is quite simple.
All right, thanks.
Yeah, can I make a comment?
Yes.
Yeah, just a quick comment. So the result about exponential decay of correlations in transverse field Ising model.
Yes.
So that can also be obtained from generalized hydrodynamics, actually.
Okay.
There's a theory about something that developed a year ago, ballistic fluctuations, now that, which actually gives exponential decay of twist fields of these non-local fields. Okay. And it gives it, yeah, for arbitrary state, and gives exactly what the thing that you write. Well, I haven't calculated it explicitly for that model. We've done it for XY model, for instance. But I think it's the same, yeah.
Okay, and so can it be applied to interacting theories as well?
Yes, it can be applied to interacting theory as well, where the formula is much more complicated, but there is a TBA like, TBA based type of formula for interacting theories as well. Yeah.
Okay.
By the way, but it's nice that you get it from form factors, by the way. It's quite non-trivial.
Is it this large deviation theory or?
Yeah. It's this large deviation theory thing, where you can get these exponential decays like that.
I have maybe more basic question. So you talk about these like non-local operators, and for finite temperature that you need essentially all excitations, or you need to consider excitations of all particles, but only excitations with mesoscopic amplitudes.
Yes.
If I understand this correctly, I don't really know how to think about the amplitude of an excitation in some finite entropy state, because I mean, you're shuffling around your particles, but it's not clear which came from where, right? You just have a new distribution.
Exactly.
So how do I even think about the amplitude? How can I?
Yeah, exactly. So when we say that, so we mean on each of these terms here. So if you isolate one term here, then you are okay. So the idea is that, so at the beginning here you have a 1 over n factorial in the spectral sum. And so in this representation here, the P has to be, can take any value. So they just don't have to coincide, but otherwise they can cross. You can also recast the spectral sum as without the 1 over n factorial, if you that the P1 will be smaller than P2, etc. Yep. And so in this case, indeed, it becomes, the question of the amplitude, I agree, becomes, because the amplitude of the excitations will be constrained, if you want, by the position of the next P. But the problem is, in this case, this constraint is very difficult to implement. So in fact, it's much, it's more, it's in a sense simpler to write, to resolve this constraint by writing things like that. And so in this case, if you exchange two particles, you really don't get the same thing.
Yeah, okay, but if you have them ordered, then you always like identify, the nth particle with the nth particle, then yeah, there is a sense of the amplitude. Okay, fair. But yeah, I don't think computationally it would work very well to implement, no.
Yeah.
Like if you try to code this, it still becomes huge.
I mean, in any case, if you take your averaging state and you want to do a finite number of particle hole excitations, you are really going to pick some of the particles then that are going to be the new holes, if you want, in the new state. And these, you are going to move them around everywhere. So, I mean, if you compare the mu and the lambda, you can indeed say where is the particle that you removed and where is the particle that you moved.
Thanks.
Okay, any more questions? If you don't mind, I would like to ask a very basic question. So basically you showed that for Lieb-Liniger, if you take, let's say, C infinity limit, and this psi dagger psi operator will somehow you only need one particle hole, two particle hole contributions. It's very different from sigma x in the transverse Ising field, I guess.
Yes, indeed.
Yeah, but then you can also map this free fermion model back to Ising model, I guess.
Yeah, because the density here will be the equivalent of sigma z and not sigma x.
Yeah, so for sigma z, you only need, let's say, one and two particle hole.
Yes, exactly.
I see. Okay.
Yes, so the analog of the density here in the TFIM would be the sigma z operator. But the sigma z is kind of trivial in order to compute the correlation function, so there is not much to say. So this is for local observable we considered an interacting theory in which you are going actually to have any number of particle hole excitations that will contribute to this psi dagger psi. Whereas in the sigma z for the TFIM, it will be only one and two particle hole excitations.
Yeah, okay, I see. And just a little bit, I'm a bit confused about your plot with S, with your dynamical. Yeah, so here you choose C equals 4, but C equals 4 is not very large. I mean, naively speaking.
Exactly. So I could have chosen something a bit larger if you want. It's just to say that for C equals 4, you have something that is already, in fact, much smaller than the one particle hole excitation. So if you take C equal 10,
yeah, okay,
it will be even smaller. So
okay, right, okay. Thank you very much.
So even for finite temperature, you predict this HCNC singularities. Is it correct?
So the logarithmic singularities are
in your plots.
Zero temperature. Yeah.
This is zero. Okay.
Yeah, this is zero temperature.
Okay. Any more questions? Okay. If not, let's thank Etienne again.